All right, let's look at low frequency response of a Mosfet, a common source amplifier. There's a quick note I want to make here, and that's on a notation your book uses. Okay, the book uses capital letters. With lowercase subscripts. For symbols. And the reason they do this is we're dealing with quantities that are functions of frequency. So when you see a capital letter again with a lowercase script, that indicates it's a it's a function of frequency. It's a quantity that's a function of frequency. So what we're looking at now in this chapter, in chapter 10, we look at the frequency response of MOSFETs and bipolar junction transistors, specifically the MOS common source and the BJT common emitter amplifiers. And what we're looking at is we're looking at the effects of coupling and bypass capacitors on the gain of these common source MOSFET and common emitter bipolar junction transistor amplifiers. Now, we're going to look at the MOSFET specifically, at least first here. And this effect, if you remember back to our just the general frequency response lecture, we said this effect only manifests itself at low frequencies. So below the mid-band, I think, is what we're talking about here. So look at it. Let's look at a MOSFET common source. I'll abbreviate common source CS, and I'll abbreviate amplifiers just AMP. Okay, if you remember, a MOSFET common source amplifier has infinite input impedance at the gate. So that's why we're doing this one first. It's easier to analyze for that reason than a common emitter or BJT. So I'm going to draw a little circuit here. V sig is a frequency quantity, okay? R sig, again uppercase, lowercase. Let's put a coupling capacitor here. C, little c1. Okay. We're going to voltage divider bias it. So I'm going to stick we'll call this RG2. So that's gate resistance 2. At least that's again, this is a nomenclature the book uses. RG1 here. Okay, here's our transistor. We've got a biasing voltage here, VDD. We've got an RS here. For source resistance, we've got a bypass cap here. Call this CS. And, oh, this is RD. This is the drain resistor. And we've got another coupling capacitor here, CC2, and that is attached to our load. And we're taking our output plus minus VO across that load resistor. So we got three capacitors here. The CC1 and CC2 are coupling capacitors. CS is a bypass capacitors. Now at the mid-band frequencies, I'm going to write this down because this is important. Let's just say 3 caps. CC1 and CC2 are coupling caps. CS as a bypass cap. And at midband frequencies, all three, we're assuming are perfect short circuits. Basically, they don't exist. They're replaced by shorts at the midband frequency. So I can say midband frequencies. Again, we'll say frequencies because midband is a range of frequencies. That's how we define the bandwidth again. All three are assumed perfect short circuits. Okay, let me add a new page here. And why did it do that? Let me blow this up here. All right, I think that'll work. I thought I had switched this over to landscape, but we're okay with this. Okay, so at again at midband frequencies, all three are assumed perfect short circuits, but we can say, however, at low frequencies, the reactances okay, 1 over j omega c for those caps, let's say for each, increases, and the amp gain decreases. Okay, so what we can do is we can look at a T model. So let's do this. You're used to using the T model from last semester, so let's look at a T model. So let's look at the T model. Okay, here's our input source. Again, we'll start on this end. The SIG. Here's that source resistance, our SIG. Here's CC1. Okay. The other side of that, okay, remember our DC supplies end up looking like ground. Okay. So VDD becomes ground. So RG1 is shorted to ground. RG2 is, I guess we could say, still at ground. Okay. We can model a dependent current source here, if I can draw it right. We can say ID. I little d is equal to I little s. Stick another resistor here. This is the 1 over the transconductance. Okay, GM. Okay, and you remember GM is ID over VGS. If you think back to earlier last semester. Okay, we've got our S here. And we've got CS. Okay. Attached to the upper side of this dependent current source, we've got RD. Again, that drops to ground. We've got our coupling capacitor, CC2, and we've got our load resistor here, RL. Okay. Our output, again, still appears across the load. Okay, we can define a couple things in here. We can define a current ID, which is just the value of that source. Okay, we can define a current here, IS. Okay. We can also identify, and I'll go through this with you, I'm just going to write them on the diagram here. We can define an impedance here, ZS, that's going to be RS. If you look at RS as in parallel with CS, so those two are in parallel, so we'll figure out what that is, what that impedance is. And here we've got, I just realized I made a mistake. This should be RG2, this resistor right here. Okay, here we've got RG1 in parallel with RG2. Okay, and just a couple notes here. And again, this is a little bit of review. To get T-model, we shorted VDD. Okay. Now, if you also remember, if you remember from last semester, I think it was in chapter 7, there was little r o, okay, and little ro was defined as the finite resistance between the drain and source of the Mosfet. So we can say transistor little ro has been omitted here. Just like it was omitted back in chapter 7 last semester, because it only complicates things, complicates the calculations, and has basically little to no effect on the performance. Let's just say N has negligible performance. Effect on discrete circuit amplifiers, which is what this is, right? It's not an IC transistor. Discrete circuit amps. And again, I'll write it in red here. R0, little r0 is the finite resistance between drain and source of a Mosfet. Again, you want to refer back to chapter 7 for that. Okay, so where are we? You also should recall the overall gain of this thing. Of this amp. Of this amplifier, okay? So we can say VO over V SIG is equal to VG over VSIG times ID over VG times VO over ID. Okay, where, and again, this is T-model stuff. I'll do this in red. We can say where VG is the voltage between the gate and ground. It's let me just scroll up here. I'm not sure if I put this on the diagram. No, I didn't, so let me add it right here. We're going to put VG right here. Okay. So that's what VG is. What else? ID is a drain current. That's indicated on that diagram. Okay, so we have to find the voltage at the gate, basically VG. Okay, we've defined it, but how do we find it? So let's take a look at that. Okay, so we can say to find voltage at the gate, VG. Okay, we had said right at the beginning here, remember the input resistance of a MOSFET at the gate is infinity. Recall, remember, whatever from last semester, input resistance of a MOSFET at the gate is infinity. So the amplifier input resistance at the gate is basically a function of the components. Okay, the resistor. Okay, the source resistance, the gate resistance RG, and which is a combination of RG1 in parallel with RG2. I'll write this stuff down, and the capacitance. Okay, so let's see, amp input resistance. So the amp input resistance at the gate is RG, and that's equal to RG1 parallel with RG2. I may have misspoke, I can't remember. But yeah, this is the input resistance at the gate. So the infinite input resistance of the MOSFET at the gate is infinity. So it's an open circuit, basically. So you just end up with RG1 in parallel with RG2. So now we can say, I might have jumped the gun earlier. Okay, using a voltage divider now. We have VG equal to the input times RG, which is RG1 in parallel with RG2, divided by RG plus 1 over SC little c1. I'm going to put that in parentheses, plus R, the input resistance of the source. So, or the output resistance of the source. So, pretty simple, right? It's just a good old-fashioned voltage divider. We can rearrange this equation a little bit here. Let me start a new page. Oh, looks like I can go now. Okay. Let's, so we can say rearranging. Okay, we can say VG over V sig, V source, is equal to RG over RG plus R side G times S over S plus, if I can get this one right. Okay, 1 over C, C1 times RG plus the source resistance. Let me tidy up my parentheses here. Okay. So what's going on here? Let's take a look at what's going on. I'm going to label this to equation 1. Because we're going to refer back to it. But, okay, we can see the effect of CC1 on the amplifier input. Okay, it's a frequency dependent function. Okay, so let's write that down. We can see the effect of C1 on the amplifier input. So we can say this is a frequency-dependent factor. So, and if we refer back to chapter 1, this is section 1.6, which again you covered last semester. We can write the transfer function. Of a single time constant I'm going to underline that, single time constant, high pass filter with a pole frequency omega p1. Okay, and omega p1 is equal to that one over c little c 1 R, okay, source resistance plus Rg. Okay, in addition to the pole, CC1 introduces a 0 at S equals 0. Okay, those are DC conditions. Remember capacitive reactance, 1 over 0. Okay. Which it should. Okay. So CC1 is a coupling cap again that blocks DC. Okay. So okay, which it should. Let's just say this. And we'll say CC1 is a coupling cap. And what we're trying to say here, and we've said this before, and you said this last semester, it's a coupling cap that blocks DC. All right, so we can make a little sketch of what we have so far. All right, I'm gonna draw. I get enough space on this slide. Okay. Okay, we're going to put magnitude in dB. What else? Omega, log scale on our horizontal axes. Okay, and we can define a curve here. And again, I'm not the best artist in the world, but I think hopefully you'll get the idea here. It's not looking too bad. Okay, we got a slope here of 20 plus 20 dB per decade in this section. Okay. We can define some magnitudes here. Make my little dashes here in red. Okay. We can show a 0 here. 3 dB down is right here. Hang on just a minute. Three dB down, let's make it, show it here. Okay, we said, I'm going to call that a negative 3 dB. That's a negative 3 dB off our midband frequency. Okay, and I'm going to show a omega P1 here. Okay. Okay, and this sketch right here, let me just write a little note here. Is magnitude of the high pass function. Okay, and I'm going to have to jump to the next slide here. We can say, and if we want to write that explicitly, switch back to this color, we can say, let's make a note. This sketch, oh, I already wrote that. Let me erase that. It's Sunday morning, I'm still waking up. Okay, we can say S over S plus omega P1, or omega over omega squared plus omega squared P1, square root of that, versus frequency omega. Okay, so that kind of takes care of it for that first bypass capacitor C1. Now we want to look at what's going on with CS. We got three capacitors.